So welcome to week 5 tutorial for the course Essential Mathematics for Machine Learning. I hope you are able to see my screen and I'm audible. Okay, so the topics that I plan to cover today would include basics of linear regression. Okay, and how whatever we have talked so far is relevant for linear regression. We will try to connect it. Okay. Then we'll also talk about logistic regression. Okay. We'll talk about the concept of overfitting and underfitting. Okay. And I think in the lecture, professor said that you can optimize your logistic regression via gradient descent, but it was not explained how. Although the gradient descent is covered in one of the weeks later on, but I'll try to just give you an idea what gradient descent is and how do you use it. Okay, because it's the most commonly used technique to optimize your parameters. Okay, and also towards the end, I'll give you a flavor of maximum likelihood estimator. What is maximum likelihood estimator? Because at many places, when you will learn about linear regression and logistic regression, you will see a different kind of motivation over there. And that motivation is through maximum likelihood estimator, or there is also something called maximum a priori, uh, posterior, so maximizing your posterior MAP estimation. So I'm not going to cover MAP today, but I'll give you an idea what MLE is. In 2 hours, I'm not sure I'll be able to cover all these topics, but I'll try to give you a fair idea of what it is. Okay. So at any time during the lecture, if you have any doubt, you can please stop me there and ask. I'll try to be a bit fast today because I have a lot to cover, but please stop me whenever you have any doubt or anything. You can either unmute yourself and speak, or you can type it in the chat box. So let me begin. Okay. So this course is about essential mathematics for machine learning, but we have been doing maths all along. So today is the first time when we are talking about some machine learning tasks. So if you'll take any basic machine learning course, this logistic regression or linear regression, this would be the first thing that would be taught there. Okay. So I'll just try to give you a brief idea of kind of tasks that we try to do in machine learning. So the broad umbrella of machine learning can be divided into 2 or 3 categories. Okay. So first category is what is known as regression. Okay, so let me start a level up. So first category you can call as supervised learning. Okay. Second one is called unsupervised learning. And the third one is called reinforcement learning. Okay. I'll try to explain what these are. So in supervised learning, whenever you have your data, you will have some X, which are your features, and you will have a Y. Y is the value that you want to predict. Okay. So you are given with a pair of X and Y, a lot of data is given to you. So you want to infer some pattern based on this so that you can predict Y for upcoming data points. Okay. So in supervised learning, you have features as well as you have the value that you want to predict for some data points. Okay. So the basic approach that you take in these kind of methods is that you approximate some function. Okay. And based on that function, you take your prediction on X, and then you take its loss with respect to Y. Okay. And you try to minimize this loss. Okay. So this is the, I think now these notations are clear. This is norm square and those kind of things. Okay. And you try to minimize this loss. This is the basic idea behind supervised learning. Okay. Obviously, you can have more sophisticated methods for different kind of data set, but this is the basic idea. Okay. In unsupervised learning, your you only have features with you. You don't have any associated label. Okay, so you don't have associated label. So for example, if you want to cluster some points, so common task over here is clustering. Okay, you want to cluster some point, then what you do? Okay, this is one task. Okay, there are other unsupervised learning tasks also, where you want to learn in absence of labels or those kind of tasks. There are quite a few tasks. Okay, then third comes the reinforcement learning. In this regime, what you have is, so you have some space, okay, where you take some action, okay, based on your action, you get some reward or penalty. For example, how do you train a self-driving car? Okay, so a way to train a self-driving car is, so currently your car will be in some state or some space. Okay, basis of that, it will take some action. So it has options to keep going straight, apply brake, or let's take left, let's take right. So it has these kind of options available with it. So whatever action it takes, based on that, it will get some reward or penalty. Okay, so reward would be that it is going smoothly. Penalty would be that it has hit some object. Okay, so the objective of this kind of methods is that you have to minimize your penalty or maximize your reward. Okay, so this is the broad area of machine learning methods, the kind of methods that machine learning community deals with. Okay, most of the tasks that you hear around us, most of the applications that you see being solved using machine learning can more or less be fitted into one of these three categories. Okay. Now, this supervised learning has two further bifurcation. One is called regression. Obviously, there can be more. I'm talking about two main. Okay, and these are the ones that we are going to discuss today. One is called regression. Another one is called classification. Okay. So let's say we have a task where you have to predict price of a house. Okay. So let's first define this. So what regression means, the y that I defined, so you will have some x comma y over here. The y can take any real value. Okay. So it can take continuous real value to be more precise. For example, let's say price of a house. So if there is some noise from the background, please ignore it. It's because of the Dahi Handi festival going on. Okay. So let's say you want to predict the price of a house, you are given with the area of your house. Let's say locality you are given. And then let's say you want to measure the distance from nearest metro station probably. Okay. So you have a feature vector like this and you want to predict the price of a house. So the price that you're going to get is a continuous value. Okay. So you can have price to be, let's say, 50 lakhs or 50.2 lakhs. So this is continuous value that we are getting. So this kind of tasks that when we solve, these are called regression. So the y that you take are continuous in nature. Okay. Whereas in classification, the y that you have are discrete in nature. And discrete also, and they can take very less number of values. Let's say they can take 10 values or 20 values. Okay. So for example, let's say you have some voter data set. Okay. So where you have a characteristic of every voter. So probably in India, if you say, you will have his age, gender, okay, age, gender, then his religion, probably it's a crucial factor in India, probably his caste, education level, those kind of things. And you want to predict for which party will he vote. Okay. So the prediction that you're making, that will be selected out of one party. Either he'll vote for BJP or probably Congress, or he'll vote for Aam Aadmi Party or something like that. So these values that you have are discrete in nature. Okay. So these are not continuous. We can't vote something between BJP and Congress. Okay. But he can get a value between 50 lakh and 50.2 lakhs. Okay. So this is the basic difference between regression and classification. Whatever I have discussed till now, is it clear or is there some doubt in it you can ask?
No, sir, got it.
Okay. So in regression, what you have to do is you have some data point, and you want to predict some y, and y takes continuous values. Okay. Okay. So let's start with this way. Okay. So let's say you have two data points. Okay. Your first value represents x, and this represents your y. Okay. And this represents your y. Let's say we plot this point. So we are given with two data points. First is 1 comma 0, second is 0 comma 1. Okay, so let's say we want to plot these points. Okay, so first point is 1 comma 0. Let's say this is this point, then this is this point, and you will have a straight line connecting these 2 points. Let's assume that this is this point. Okay, this is this point. Okay, and this is this point. So now you have fitted a line that passes exactly through these 2 points. So if these were your training data points, you know that these points lies on this line. So let's say now somebody asks you what is the value of half that you will get corresponding to this. So you can look at this line and say the value that I'm going to get is, let's say, half comma half. Okay, this can be some other value. Please check. I'm not sure, right? So this is the kind of thing that you can do if your line passes through these points. Okay. So what you want to do is, so whatever data points you are given for training, you want to set a line through these points. Okay. So if you are given with two points, and so your x over here is just one dimensional. Just a second. I think I need to disable this. Give me a second. Okay. It's visible. Okay. So what I was saying was your x is one dimensional and y will always be one dimensional. You want to predict one value. Okay. So the space in which you want to fit this line would be R2, right? So again, so if you have these data points, you want to fit a line for 3 dimensional, you will say that you want to fit a plane and so on, so that it passes through all your points. Okay, this is your ultimate goal that you want to achieve, that it passes through all the points. Okay, but let's look at this example. Let's say this is the data set that was given to you. Then what do you do? Okay, so let me plot these points. Okay, so let's say this is given to be, again, these are the same points. So this is 1 comma 0, 0 comma 1, and 0 comma 0. Now, no matter what you try, you can't fit a line passing through 3 points, right? You can get a unique point passing through only 2 points. If you have lesser or more number of points, okay, then you can't do a lot. Okay, then you are in trouble. Okay, so what to do in such situation? Okay, so what is proposed is you draw a line, okay, and you measure the distance of all points from this line. Okay, so these are the distance of these points. Okay, let's say this is error 1, this is error 2, this is error 3, right? And then what you do is you try to minimize the squared error, right? Sum of square error. You try to minimize this thing. Why square? Because error can be negative and positive both. We want error to be counted as positive, so we have squared it. So we should minimize this. So you want to find a line so that the overall error that you obtain on all the points when you calculate its error from this line is minimum. Okay, and this is the goal of regression. Okay, now because we are fitting line, which is obviously linear. Okay, so line and linear are same, loosely speaking. Okay, so this method is called linear regression when you try to fit a line through these points. Right. So when you fit a line, it is called linear regression. When you fit a polynomial, it will be called polynomial regression, and so on. Okay. And why is it very important? Why do every machine learning course starts with linear regression? The first reason is it is very simple. Okay, it's easy to understand, it's easy to calculate, it's simple in every manner. Okay, but don't go on its simplicity, it's a very powerful tool. Okay, okay. So what I mean by it's very powerful is that we will talk later on that it can also be used to approximate nonlinear functions. Right now we are just looking at linear lines, but with some modification, using the same technique, we can extend this to nonlinear approximation. Okay. Another reason is that it provides some interpretation. Okay. So you have a line on one side of it, you are saying that it's some label. On other side, you are saying it's some other value. So it provides some kind of interpretation. Okay. Okay. Let's ignore this picture because I've already explained this error thing. Okay. So let's look how we can sort of go about linear regression. Okay. So let's say you have a data point of similar form. So you have x comma y, where x is one dimensional, right? So if somebody has given you a bunch of data point, how do you approach this method? Okay. So what now you will try to do is you want to fit a linear line. Okay. But you don't know which linear line you want to fit. So you don't know which linear line. Okay. So what is the arbitrary equation of a line in one dimension? So if you remember, arbitrary equation is given by y is equal to ax plus b, right? So any line in this two-dimensional plane can be obtained by this y is equal to ax plus b if you keep changing your a and b. Okay. So our goal is to find a and b such that the line that you obtain is at the minimum distance with respect to this. Okay. So let's say uh, you have this data point, right, where your x is this and y you have obtained to be this, and z is this blue line is the original data, so original line from which these points were sampled. Okay. So what is the error that you see? You have some error, let's say E1. Okay. So now what you will do is, let's say you have some, you approximated your line by ax plus b. You call this as f. So f is given by ax plus b. Okay. And you have y associated with it. So what you will do is you want error between f of x and y. You want your f of x to be as close as possible to y. Okay. But you don't know what is the value of a and b. Okay, so the error is given by f of x minus y whole square. Okay, and you will sum it over all the data points that you have. So in machine learning, you will not have only one data point, you will have many data points. So this is the overall error that you have. This kind of error is called mean square error. Okay, so you divide by 1 by n also, the total number of data points. So this is called mean square error. Okay, and this is the most commonly used error for a regression task. Now you have to minimize this thing. Okay. How do we minimize? I think that is discussed in the lecture. And the minimum solution is given by A transpose A inverse A transpose B. We will talk about it, how the we reach there, but right now I'm just mentioning it that it can be obtained in closed form. So when I said that this method is simple, you need not use fancy methods like gradient descent, which gives you approximate solution and those kind of things. you have a closed form solution which gives you exact solution for your parameters. Okay. So whatever value you will obtain would be your value for A and B. So this B is, let's call it Y for the. Okay. So any doubt in motivation for this linear regression? What is linear regression? What is the error involved? How do we solve it? Any doubt in this? Please ask like that. Because now I'll go to a more non-trivial topic called underfitting and overfitting. I think before going to underfitting and overfitting, let's look at some extension of linear regression. Okay. Let's say whatever we discussed till now, we said that the data points lie on a line. Okay. But let's say when you actually saw your data point looked something like this. Okay. Something like this. Now, if you'll try to fit a line through it, you're certain to make a lot of error. Okay. So, in other words, you can say that the line is not a good representation for this data. Okay. Right. So, what you can do in such situation? Okay. So, what you can do is you can see that this is some sort of sine function. Okay. Sine or cos, and it's translated a bit. Okay. You can see that thing. Okay. So, what you can do is you can include a feature having nonlinearity. So right now, how your data looked like was, let's say you have this x1, you have corresponding y1, then you have x2, you have y2, and so on. This is how your data look like. Okay. Now what you do is, in between, you slice in something like, let's say, sine of x1. So this is another feature that you have, and you name it something, some other feature. Okay. So let's say this is feature 1, this is feature 2, and this is your y. Okay. So you can calculate sine of x1 for every x1. Now you have a data in higher dimension. Earlier you have data in one-dimensional feature space and one-dimensional prediction space. Now you have a two-dimensional feature space. Okay, containing f1 and f2. Right. Now what kind of line or plane you want to fit? Now you want to fit something like a times f1 plus b times f2 plus c. This is your f of x. Okay, and a, b, c are the values that you want to find out. Okay, I hope this is clear. So you can have all sorts of non-linearity that you can induce as a feature based on your data set. You can have something like x square, okay, x1 square, so feature 1 square, or you can have feature 1 into feature 2, you can have feature 1 square plus feature 2. All sorts of non-linearity you can include on your features, right? And then you can obtain your results. So as I said, this simple trick, whatever we learn from linear regression, can easily be extended to non-linear setup by including the required features. Right? This is what you will do. Okay. Now what we will do is something called as overfitting and underfitting. Okay. Again, this is not a machine learning course, but I want to motivate you for regularization. So I'll give you an idea what underfitting and overfitting is. Okay. Okay. So let's say this is your XY coordinate. Okay. And you have a data set like this. Okay. Now let's say you want to fit a line to this. Okay. So how would a line look that you would fit to this? Probably something like this. Maybe I'm not very accurate, but it would look something like this one, right? When you want to minimize the error. Okay. You can clearly see that this is nowhere a good fit. Okay. So what do I mean? If we just take our linear features, we are not getting a good fit for the data. So this kind of model, so we model our setup using linear function. So this kind of model is set to underfit. Okay. So what I mean is, so this kind of model is not sufficient to capture the essence of the data set. Okay. So this is too weak to, the model complexity is very weak, or model complexity is low to be able to capture trend in your data. Okay. So on the other hand, so let's say when you look at the initial part, right? You see that the line was going smoothly, and then there is a lot of hodgepodge. Okay. So if we kept going on this line, we would have obtained something like this, right? So what has happened over here is whoever person was recording this data set made some error while recording the data. Okay, and that is very common. So we are humans, we make error. So whoever was like creating this data set at this point in this section, he made some error. Okay, and you will see that training data set are prone to such errors. Okay, now let's say you included lot of nonlinear features. By that, what I mean is, let's say you included x1 square, x2 square, and then let's say x1 square plus x2 square. You also included x1 cube, x2 cube, and so on. Let's say you included till power x to the power 10. Okay. Then if you increase the model complexity so much, what will happen is the line that you will draw will fit your data points exactly. So it will make zero error on it. Okay. But we wanted to learn the black line. We have learned the red line instead. Because we had some noise or those kind of things in data, we learned the red point. Okay. Now, let's say in another example, this orange cross that I have over here was actually by mistake marked here. So if you see the distance from this line, black line, I'm making less error, right? So if now I try to fit this again by this, let's say 10-dimensional polynomial, what will happen is I'll again exactly fit this, right? And so on. See how much error am I making? Okay. So as I increase my model complexity, even small changes, okay, small changes in training data can lead to large error on test data. Training the data. I would have meant training on the training data set. So I'll like briefly explain what is training data set and test data set. Then I think it will be more clear. But for the time being, just remember that if you choose very high complexity model, then you can do very well on the training data, but you will make large error on test data. Okay. So this kind of setup is called overfitting. So when you choose too complex model, you will overfit. When you will choose when you will choose less complex model, very less complex model, something like linear model, then you might underfit. Okay. Now, I think what does it mean training the data set? I think if I'll explain it this way, yeah, my answer would be clear. So whatever data set that you get in machine learning, I think my battery is low. I'll connect the charger. Okay. Okay, whatever data set that you have, you divide it into three sets. First is called training set. Okay. So when I talked about this loss function, right, this error mean square error, this error you calculate only on your training data set. Okay. So because you are minimizing your error on this training data set, we say that we are training the model on this training data set or on this particular data set. Okay. By so what you asked is what do we mean by training on the data set? By that we mean that we have minimized the error for that data set. Okay. And last one is called test data set. I'll come to the middle one later on. Okay. So what do I mean by test data set? So when once you have trained your model, you don't want to keep your model to yourself, right? You want to test it in real world. Okay. So in real world, you will see a lot of unseen data set. Okay. And those data set are known as test data set. Okay. So here you don't minimize your loss or anything. You have already learned the value of, let's say, for example, A and B, these parameters you have already learned, and during testing, you just want to use them to evaluate your model. Okay. For example, let's say you train a model where you take picture of an X-ray and you want to predict whether some disease is present or not. Right. So during training, you will have lot of X-rays that you will see. You will try to minimize the error, and then you will deploy your model in some hospital, right? Where a patient, whenever he gets his X-rays done, your algorithm will automatically tell whether there is some risk of some disease or not, and then can send this report to your doctor. Okay. So during your testing time, you don't have any model optimization or those kind of things. And also, you want high accuracy during testing. Okay. Even if your model is not doing very well during training, you shouldn't be worried about it. You should be worried if it is not doing well during testing. Because here it is when it is important. So let's say you're deploying it in hospital and you make some error, then it's a like call about life of some person. Okay. So you don't want to make error during testing. During training, it's more or less okay. So nobody is going to ask you how well you are doing on your training data set. People are going to ask you how well you are doing on unseen testing data set. Okay. There is something that I skipped that is known as validation data set. Okay. These are used to tune hyperparameters. So there are no hyperparameters right now, but towards the end of the lecture, we'll have some hyperparameters. Then I'll tell you what do I mean by tuning hyperparameters. Okay. So the takeaway of this discussion is if you take basic models, okay, then you will do underfitting. And if you do too complex models, then you might overfit. Okay. Okay. So one more small analogy that I want to draw is, okay. So, okay. So I think always like to view my model optimization this way. So when I try to find parameters, what I do is, let's say this way. So what you have in machine learning is you have some data points. I'm just giving you analogies, whatever is best understood by you, you take that and you can use the same thing for using this on other machine learning tasks. So let's say you have some training data set X. So you have a bunch of training data set Xi and Yi. When we train, what we do is we define some loss. For example, in the linear regression, we define mean square error. That was f of x uh, minus y whole square sum divided by n. Right? It was something like this. This is that you want to minimize. Okay. And minimize over what? Minimize over this f. So you want to search for an f, right? Which can minimize this error for you. Okay. So how far can you search for f? Okay. So where do you search for f? This is an important question. Okay. Where do you search for f? Can you search over all possible functions that you have? The answer is no, right? You can't search over all possible functions. So what you do is you search over some limited space. Okay. Okay. For example, when you do linear regression, you search over all linear functions. Okay. So when you do linear regression, you search over all linear functions. Okay. When you, let's say, include a term like x1 square through features, okay, then you search over, let's say, all quadratic function. Okay. So what I'm trying to say is, as you increase the model complexity, or I would say, as you keep on increasing your, let's say you add on x1 square, then you go to x1 cube. So this is increasing the model complexity. Okay. So as you increase the model complexity, your search space becomes bigger. Becomes bigger. And it can also be said vice versa. So if your search space is large, this would imply that your model complexity is high. Right? And vice versa. If your model complexity is high, your search space is large. And also the counter positive is true. If your search space is small, your model complexity is low. Okay. And this kind of, so if your model complexity is very high, this can lead to overfitting. Okay. So the problem of this overfitting and underfitting can be solved by restricting your search space sufficiently. Okay. So you don't want your search space to be too small, but you don't want it to be too large too. Okay. I'll get back to this. Okay, right now let's take a sort of, let's solve some questions here. Then we'll go to how do we tackle underfitting and overfitting. Okay. Another thing that is here is, so let's say you have some data set. Let's say this is, you have two features, and let's say you have I, right? And let's say you have data points x1 with some value, x2 with some value, x3 with some value. Okay. Now, if you make a matrix out of these data points containing all features, okay, this is all feature, and you create another matrix. I am not able to change color. Yeah, you create another matrix containing just your y. Okay, and you name this thing as B. Okay, I'll use a smaller pen. You name the second vector matrix as B, and you name this big fat feature matrix as your A, then the solution to your linear regression problem having minimum error, least square error, is given by this. So your value for weights is given by A transpose A inverse, A transpose B. You know your A, you know your B, you know how to calculate inverse, and this is your A transpose. Okay. So this is the closed form for least square error. Okay. Okay. So I think I have taken slide D2 from the way the content was taught in lecture. So let's solve these questions which are based on things taught in lecture, so that things are more related to whatever I have discussed. I'll try to read both these things here, and then yeah, I'll try that. Okay. Okay. So first question is, given the linear system of equation, right, which of the following is true about this thing? Okay. So now, if you see these two system of equation, do you remember the like class in a class we did something like dimension of subspace? Right? I'll try to link this problem with there also. But first of all, see that you want to find value of three variables, right? But you have only two conditions to govern. Okay. So what you can do is, let's say you want to calculate x from here. Okay. So x can be given by b minus 2z minus 2y, right? v1 minus 2z minus 2y. And y from the second equation can be given by v2 minus 3z minus 5x. Okay. Now you replace the value of x from the above equation in this, then you will get y is equal to b2 minus 5b1. This is plus 10z1, so minus 7 plus 7z, and this would be plus 10y, right? So yeah, so this can be given by y is equal to minus 1 by 9. B, this is 9 not g, b2 minus 5b1 plus 7z. Okay. So you have obtained the value of y in terms of z. You can similarly, if you plug in this y in this, you can obtain some x in terms of z. Okay. So z over here turns out to be a free variable. Okay. What do I mean by free variable? Is if you take any value of z and you put it in here, you can get a value of x and y so that it will satisfy this equation. So you don't have any restriction on value of z. Z can take any value and you will have corresponding x and y. Okay. So as you can take any value of z, such a system will have infinitely many solutions. Because you can take any value of z and you will have corresponding x and y using this formula, whatever we have written over here. Okay. So when you have lesser number of equation is less than the number of variables, then you have infinitely many solutions. Okay, so this I think is the correct answer, that if your system have this kind of setup, then you will have infinitely value of infinite number of solution for any given value of v1 and v2. Okay. Okay. Now this is the question related to whatever we discussed. So this is your feature matrix. So in your data set, you have three data points, 0, 1 with y value. So this is feature 1, this is feature 2, this is y, right? 1, 1, 0, this is 6, this is 0, and this is 2, 1, and 0. Okay. So we have constructed A from here. This is your A. And B we have constructed from here. Right. So what was the solution? Solution was, your least square solution is given by A transpose A inverse A transpose B. Right. So let's take A transpose A. This is 0, 1. Okay, so 0, 1, 2, 1, 1, 1 multiplied by 0, 1, 2, 1, 1, 1, and this is given by 0 plus 1, 0, 1, 4, 5. This is 3, this is 3, this is 3, right? And then you can find its inverse. This is 15. This gradient is given by 15 minus 9 is 6. You swap these entries. Okay. Yeah, you swap these entries, right? And you multiply the off diagonal ones by minus. Okay. I think this is how you do. So this is A transpose A inverse. Then you multiply it with A transpose and you multiply it with B. You will get your least square solution. Okay. Okay. So this question says, for a linear system Ax is equal to B, A has order 4 cross 7, the number of free variables it is asking. Okay, so if A is 4 cross 7, so it has 4 rows. So each row corresponds to an equation. Okay, and it has 7 columns, and each column corresponds to a variable, right? So we saw in the previous two PDFs example, if your number of equation is less than number of variable, then you have some free variables. So how many variables are free is given by 7 minus 4, which is 3. So here we saw that because we had two equations, we could get only two non-free variables, others will be free. So here we had 7 variables and 4 equations. So there would be at least 3 free variables. If you have two dependent equations, then again you can have more free variables. But right now we can pick 3. So at least 3 free variables. Okay. Any doubt till this point before I move to next question? Okay. I said today I might be a bit fast, so please ask and stop me wherever you feel like something is not clear. Okay. So this is a data set that is given to us. Okay. And we want to apply a linear regression. So these are called parameters. So earlier also I wrote ax plus b, y is equal to ax plus b. So these a and b are called parameters of your model. So these parameters need to be learned. And this is just a name for these coefficients. So these are called parameters of your model. So here we have theta naught and theta 1 as our parameters. Okay. And the training data is given by this table. The cost function or the loss function is given by this. It is asking what is j of 2 comma 1. Okay. So it is giving us value of theta. Theta is 2 comma 1. Then what does your h of theta become? This becomes 2 plus x, right? So let's calculate h of x for this given theta. We will have 2 plus x is given by 8, 7, 12, 5, right? And now what is j theta? J theta is sum of all errors divided by 2m. Okay. So the error over here is 8 minus 7 square. 8 minus 7 square is 1. Here we have 3 square is 9. Here again we have 3 square is 9. Here again we have 1. So this is 20, right? Total error is 20. We have to divide it by 2m. M is the number of data points. So we have 1, 2, 3, 4 data points. So we'll divide it by 8, and this is given by pi by 2. Okay. So this is the total error that you are making if you choose your theta to be 2, 1. Okay. Okay. So if you have any doubt, you can ask. Otherwise, we can take a break of 4 minutes and we can start again at 7 o'clock.
Now, how is this h of x derived?
So we were given that. So we have to find j of theta for theta given to be 2, 1. Okay. So theta is your parameters, right? And how you
Okay.
obtain h of theta is mentioned in the question. This is theta naught plus theta 1x. So 2 times 1, theta naught was 2, just comparing vector to vector, and theta 1 was 1. So h we obtained as 2 plus x.
Okay.
Okay. Okay. So, okay, we'll start again at 7 o'clock. You can take a 3-4 minutes break. Okay, I'll start again. So, okay, next, what we talk about is something called regularization. Okay, so I'll try to motivate it in two ways. Why is the regularization important? Okay, So before just discussing these questions, what I mentioned was, if my search space is small, that would mean my model complexity is small, less. Okay. So let's say you chose a polynomial of degree up to, let's say, 6. Okay. A polynomial of degree up to 6. Okay. And yeah, so you chose a polynomial of degree up to 6, and you see that you are overfitting. Okay. But you also know that if you take something, let's say a polynomial of up to degree 4 or 5, you are not performing very well on the data. So by that I mean you are sort of underfitting. Okay. So you know that this much model complexity is required, right? But then also you are sort of overfitting through your data. In that situation, what you can do? So the solution to that is something known as regularization. So idea behind regularization is, so let's say you have a polynomial of a degree up to 6. So you will have something like w1 plus w2x plus w3x square, so on till w7 x to the power 6. So you will have a function like this where you have to learn w1, w2, w3, w5, w7, right? This is how you do linear regression, right? Now, right now, what you are doing is you were allowing w1 to w7, right, to take any value. Let's say what I say is you allow these values to be only small. Okay. So if you take large value of w1 to w7, I'm going to penalize you. But if you take small values, you are fine with it. By that, what do we do is, now we have reduced our search space, right? How? Because this set of function over which we can search is smaller, because now we just want w1, w7 to have smaller value. So we have restricted or confined our search space. Okay. So because we have reduced our search space, now the sort of model that we fit, the model complexity is low, and we can avoid overfitting, right? How do we ensure that we get W1 to W7 small? We will talk about it. But right now, this is the idea of regularization, that whatever is the weight of your parameters, whatever parameters that you learn, it should take small values. And this is a very like most useful method to elude your this overfitting. So if you want to get rid of the overfitting, you should use regularization parameter. Okay. Now this plot I have, the red curve is something like 5x cube minus 5x square minus 5x plus 5. So I have allowed coefficients to be high. Okay. Another one is x cube minus x square minus x plus 1. Okay. So if you look at the curve with the higher weights, or this 5, okay, the curve is taking sharp turns, right? The curve is taking sharp turns. Whereas the other curve, if you say, it is taking very small curves. Okay. So this is what we want. So we want functions which do not take sharp turns. So this is also what we achieve via regularization. Okay. So how do we regularize? So you know, right, till now I'm sure that you know that the loss function for your linear regression is given by 1 by m, I is equal to 1 to m, right? F of x I minus yi whole square. This is the loss function that you are given, and this is what you want to minimize. We have discussed this so far, right? Now what you do is, let's say your f was something like w naught plus w1x plus, let's say, wn(xn). In the loss function, you incorporate a term with norm of w square. What does this do is, so if your w naught to w1 are taking large values, then you will increase your loss. But you want to minimize this loss. So it will force that the values of w1 to wn that you're taking should be small. This w is nothing but your vector of w naught, w1, and wn, right? And you're taking its norm square. Okay. So including this term is known as, this is how we regularize, right? And we also have a parameter lambda that we multiply. Okay, it's not just the norm, but it multiplied with some parameter. This parameter is generally, let's say, 0.1 or 0.01. Okay, and this parameter is known as regularization parameter. Okay, and this regularization parameter is a hyperparameter. Okay, so whenever you hear the word hyperparameter in machine learning, so these are the parameters that you don't learn during sort of training. So you will fix one of the values for this parameter. Let's say you fix your lambda to be 0.1. Okay, you will learn your model. You will learn your model using the fixed value of your lambda, right? And then you will test your performance on validation set. So earlier I said we split our data set into three sets: train, validation, and test. I didn't explain how do we use validation. Now I'm explaining. So we test on validation set, and based on the accuracy on your validation set, you tune your hyperparameter. So what I mean by that is, now you will record this validation set, this test error on your validation set, you will write it down somewhere. Then you will change the value of your parameter lambda. Okay, let's say you got validation error. Oh, just a second. Let's say you got your validation error to be v1, right? When you took lambda to be 0.1, right? Then you again took lambda, let's say 0.01, and you got some validation error v2. So you will compare all these v1 and v2, and you will choose the lambda which gives you lowest validation error. Okay, this is how you do hyperparameter tuning. Okay, there are more methods which are k-fold and those kind of things. That is more better discussed. That will be more better discussed when you do some machine learning course of those kind of things. Okay. Okay, so this is what was there about regularization. I have some more content on regularization. Okay, so whatever regularization that we have talked till now is known as ridge regression. Okay, so if you have your loss, something like I is equal to 1 to m, 1 by m, f of x I minus y I square, plus you take norm square of your w, right? This form of regression is called ridge regression. It's just its name. Okay. Okay. You also have another kind of regularization, which is called as lasso regularization. Okay. So your loss term over there is something like I is equal to 1 to m. The first term is same, right? In the second term, instead of having two norm, you take one norm of your weights. Okay. So you have lambda again over here, lambda over here also. So yeah, I changed that lambda thing. Lambda would be there. Okay. That's just the habit of missing. So lambda will be here. So the second one, when you take one norm, is called lasso regression, and the first one is called ridge regression. Okay, and yeah, I have some time. I can explain some geometry behind it that can be slightly interesting. Okay, let's try to see geometry behind it. Okay. Mhm. Okay, I'll try to explain it. I'm not sure what kind of justice I can do, but I'll surely try my level best. Okay. Okay, let's say you have a model. So you might have heard somewhere, first of all, I want to make this comment is, you might have heard somewhere that the weights or the parameters that you obtain using lasso regression are generally sparse in nature. Okay. I also mentioned it in, I think, first or second lecture when I was talking about norms. Okay. So whatever weights you obtain using this are generally sparse in nature. Okay. Why do we say something like that? I'll try to explain it geometrically. Okay. So let's see how much justice I can do. Okay. Right now, let's forget about regularization. Okay. Let's say I have a one-dimensional feature. So I want to approximate it via a line. So this would look something like W1 plus W2 times X. This is just Y is equal to B plus AX, right? I have just now using a more sophisticated notation, W1 and W2, because these are weights. Okay. So you have some bunch of data points, right? You have some bunch of data points. Now, what you will have is, okay, yeah. So the loss right now would be given by something like 1 minus m I is equal to 1 to m f of xi minus yi square, right? Now these yi's are sort of fixed. Okay. So let's say these yi's are sort of fixed, right? So yeah, this point I'm not sure. Like, okay, I am sure, but let me see if I make sense. Okay. Now we want to draw some contour. Okay. So what I want to do is I want to fix a value of loss. Okay. Let's say I want to fix a value of loss is equal to 1, and I want to plot all the points, so all the values of W1 and W2 for which my loss is 1. Okay. So what I'm saying is the contour that I'll draw would be a circle. Okay. So on this circle, right, the value of my loss is 1. So you can see that this is sort of a circle. So this is something like W1 plus W2 minus X, sorry, W2X minus yi centered around some points, right? This is like A1 minus X whole square plus B2 minus Y whole square. So this is a circle centered at some point. It is an equation of that type. What I'm giving you more is these will be circles. Okay. So if you fix your loss to be 1, you will obtain circles. Now, if you, let's say this is the point where you get your minimum loss. You get your loss to be 0. Okay, this is the point. So starting from here, if you keep drawing circles, you will keep increasing the loss. Let's say this is 1 by 4. Let's say this is half. And you will keep getting concentric circles. Or maybe something will happen. Okay. So you will keep moving out and you will keep getting circles like this. Okay. So let's say somebody has not used regularization. Okay. Somebody has not used regularization and he has something that can minimize the value for you. Okay. So he will reach to this point, This point is your this minimum point. Okay, he would be able to reach your minimum point. But now what I'm saying is I want to include regularization. Let's say L2 regularization first. Okay, if you remember, I said for L2 regularization, let's say your if you want your norm L2 norm to be 1, this looks like a circle that we did in, I think, first or second class. Okay, so this is just your this is, I think, easy to see also. I'll just show you. Okay, so this is just W1 square plus W2 square is equal to 1, right? Okay, so this would be a circle, something like this. Okay, right. Now, when you include your regularization, what happens is now you are not allowed to search over the complete space, right? You are allowed to search only within this blue shaded region. Okay, because you want your W norm to be less as possible. So let's say you want your W norm to be 1 or lesser than 1. Okay, then you are allowed to search only within this space. Okay, so what you do is you keep on increasing your loss. I'm growing these circles bigger. That means I'm allowing my loss. By loss, I mean this value to be large so that I can be within this region. So what is the least value of loss so that I can be within this region, right? And my this loss is also minimum. So you can see that we have intersected at this point. So this is the value that your regularized least regression will give you. Okay. Okay. So this is clear that your regression will give you this point if you want to minimize your regression loss. Okay. Now let's look at lasso regression. I hope I'm making sense. Wow. I hope that. Okay. Now, if you don't remember, I'll just draw for you. For lasso regression, your unit circle looks something like a trapezium, right? So what I mean by unit circle or this kind of thing, you can sort of revise it. But yeah, I'll just, so these are pointed points, right? I'll just draw the outline also so that it's more clear. It is pointed points, right? Okay. And what is this? This is just a second. This is your set of points for which your one norm is 1. Okay. This is just those points. Okay. Now, again, let's say this is your point where you would have obtained your minimum if you didn't do any sort of regularization. Okay. We start drawing concentric circles from here. Okay, I'm drawing concentric circles. I'm drawing concentric circles. Okay. I'm increasing the size of my concentric circle. These are not perfect circles. Yeah, right, because of my drawing, but these would be like that. Okay. You can see the point that I have hit, this point is on the corner. Okay. So in case of lasso regression, the point that I hit is on corner. Okay. So the weight, if you will see over here, what is the weight? Let's say this is a unit square or the unit, unit circle for this one norm. So the point is 0, 1. Whereas in case of ridge regression, you had non-zero values for both these W. So this would be something, right? But both are non-zero. Okay. Whereas in case of lasso regression, you got one of the values for your weight visible. Okay. And I did a small cheating over here. So when you will get this kind of thing is, let's say if I extend this line, okay. So I started at a point within this region. So this region I'll draw. Yeah. So if you see this region, I started within this region and I landed up on that point, right? So what I'm saying is, if I started anywhere in this region, okay, I will land upon these points. Okay, I started at a similar point over here also, but I didn't landed on this corner point in case of ridge regression. Okay, and what extra we have is, let's say we extend this line from all the sides. So if you started from this portion now, this portion that we have, you would have landed upon this corner point, this corner point. Similarly, if you did something like this, you would have landed upon this corner point. So for here, your corner point is this. Similarly, for here, your corner point is this, right? So what I want to say is, for a large portion, if your minima lies in these regions, so these all green shaded regions, whatever portion I have shaded by green, right? If your minima lies in these regions, you will hit something that is a sparse vector. Okay, and you see that this portion that we have left out is very small, and this portion is much larger as compared to whatever strips we have left out. Okay, so that's why people say that lasso regression leads to sparse weights. Right. I hope I was clear. If there is any doubt in this section, please ask right now. Was I able to make this clear? Why this was not in the lecture, but it was mentioned that we'll get sparse vector. So I thought I might include it because it is not generally covered either in machine learning course or in mathematics. So if there is any doubt, you can ask. So I hope I was able to make it clear. Why do we say that when we do lasso regression, we get sparse vectors? Okay. Okay. So okay. Now one more thing. I think this closed form was not in the lecture, but I want to include it because whenever you implement it, will make your life much easier. So we know that when you try to do linear regression, so the least square solution is given by A transpose A inverse, A transpose B. This is transpose, sorry, yeah, A transpose B, right? This is your least square solution for linear regression. So if you apply a ridge regression on top of it, so with loss you include lambda w square L2 norm, then your closed form solution becomes this. So in the first term you have plus lambda I, right? Rather than taking inverse of A transpose A, you just take the inverse of A transpose A plus lambda times I, and this is your closed form solution for ridge regression. Okay, so this is a small like tip from my side, that even when you do regularization, L2 regularization, you can have a closed form solution in linear regression. Also, one extra thing that we have that I'm not going to prove here. So A transpose A inverse, you are not guaranteed that your inverse exists always. Generally, in real life data set, the data is pretty skewed, so your inverse will exist. But here, you are guaranteed that your inverse will exist. Okay, so you are always guaranteed in this case that your inverse will always exist. So you need not worry about invertibility of this matrix also. Okay, so if you apply, you should go for ridge regression rather than linear regression. Okay. Okay, so whatever solution till now, what we have talked about is related to when you have more number of data points, right? So it is a fat matrix, but in this direction. Okay, and so this is more number of equation and less number of variable. Then this is your solution that was given. Now this minimum norm solution is given for the other situation. This is not very much used in machine learning, but I'll tell you. So if you have more number of variables and less number of equation, okay, so something that we saw in two examples that we did above, this example or that 4 cross 7 example, right? So in that case, your solution is given by A transpose A inverse. Okay. So you're just the positioning of your A transpose changes, and rest everything is same. And then B, obviously. Okay. This is your minimum round solution. Okay. Okay. So I have not a lot of time left. I think, yeah. So I'll go to logistic regression. Okay. Okay. So as I mentioned, yeah, somebody has to say something. No. So the name of logistic regression has regression in it, but what I want to mention is this is not a regression technique, but a classification technique. So don't get confused by the name. It's a classification technique, not a regression technique. First thing. Okay. Second thing is, so in classification, what you have is, okay, let's see what we did in regression. So let's say you had some points, right? Uh, Something like this. You tried to fit a line that minimize the errors. This is what you did in regression, right? Now, in classification, you have two kind of data points. Let's say this purple crosses, and let's say another one is uh, green circles. Your goal over here is to find a line so that on one side of it you have all the purple crosses, and on the other side you have all the green circles. Okay. So, okay. Uh, I'll try something. This, I think, concept is necessary. So I'll try to give it to you. Okay. So everybody knows what is line x is equal to y, right? So x is equal to y line is given by this line, right? Something like this. Okay. So what is y over here? Y is 1 times x plus 0, right? This is what is y. Or let's write it in form that we have been writing, 0 plus 1 times x. So w naught plus w1x, right? So 0 plus 1x. Right? This is my line x is equal to 1. So if I make a vector out of it, the vector is given by 0, comma 1, right? I think I'm correct. Just okay, sorry. I'm sorry. Okay. So this is my line that I have, y is equal to x, let's say. Okay. So what is this y is equal to x? If I write it as, it can be written as x minus y is equal to 0. If I take its coefficient, okay, if I take its coefficient, then it is 1 comma minus 1, right? I apologize for the earlier hiccup, but this is 1 comma minus 1. So what does this coefficient represents? Okay, what does this vector represent? So if you look at this thing, if you take a normal, if you take a 90-degree angle, then you can see that this line is nothing but, so if you just arrange your y and so if you just take the other side, what you will have is this x direction is -1 and y direction is 1, right? So it's just the, if you would have written it as y minus x is equal to 0, right? So this vector gives you the perpendicular direction to that line. Okay, this is one thing. How is this useful is, if you take any point on this side, okay, now this is x plus y, let's say this is point 2 comma 1, right? And you take its dot product with this line, this whatever is the perpendicular direction. Okay, let's take the dot product. What do you get? 2 minus 2 plus 1. Okay, so this is given by, I think I drew the, okay, this is -1. Okay, now you take any other arbitrary point also, let's say 3 comma 1, right? You will get -2. So what I'm saying is, if you take all the point on one side of a line, okay, and you take the dot product with this perpendicular direction, okay, you are gonna get negative. And on the other half, you will always get this dot product to be positive. Okay, let's say take this point 4 comma, this is, okay, yeah, I think this point is not 2 comma 1, this is 1 comma 2, right? So it would be 1 minus 1 plus 2, that is plus 1. Similarly, 1 comma 3 will give you plus 2. So on this side you have all the positives, and on the other side you have all the negatives. Yeah. Okay. The point is that on one side you will have all the positives, and on the other side you will have all the negatives of a line. Okay. So just to summarize, because there was a lot of confusion. So if you have, let's say, a line w1x1 plus w2x2 is equal to 0, right? And if you write w1, w2 as a vector, then this is normal to your line, right? And all points on one side will give dot product with this w1, w2 either to be positive or negative. So you can't have 2 points on same side having positive or negative. Okay. So this is the idea that we use for classification. Okay. So what we do is, we try to find a line so that all the points on one side are of one type and all the points on one side are of other type. Okay. So can you relate these two things? What do we get over here is that all the points on this side have dot product to be positive and all the points to have this dot product to be negative, right? So can you relate these 2 points? So the relation that you get is, for all the purpose cross data points, okay, you want that their x transpose with this weight that you have is greater than equal to 0, and for all your green circles you want that your x transpose w is less than equal to 0. Okay, this is what you want. Okay, so let's now discuss about something that is known as sigmoid function. Then I think it would be more clear. Okay, so just remember that this is what you want, that x transpose w is greater than equal to 0 for all cross points, and x transpose w is less than equal to 0 for all these points. Okay, now let's look at sigmoid function. This is what is known as sigmoid function. Okay, let's try to plot its curve. Okay, so when you have x0, so this value would become 1 divided by 1 plus 1 half. Okay, so at x0 it takes value half. Okay, Now as your x tends to infinity, okay, so this value would become 0. So your value would tend towards 1. So something like 1. This is 1. So x would tend to 1. And if your x tends to minus infinity, this value would become larger and larger, and your value will tend towards 0, right? So you have a curve something like this S-shaped curve, okay, for this sigmoid function. Okay, this is something that is your sigmoid function. So for 0, you have value half. As you get positive, you reach towards 1, right? And as you go left, you reach towards 0. Okay. Now let's say we rename these class. Okay. Rather than calling them purple cross and green this circle, we can't do calculation with purple cross and green circle. We rename them as class 1 and class 0. Okay. Okay. So now see carefully. If we calculate S of X transpose W, okay, what is it? This is 1 divided by 1 plus e to the power minus X transpose W, right? So if my X transpose W is greater than 0, right? What I want is that I should predict 1. Okay. So if my X transpose W is greater than 0, what is the value that this S of X will give? So you can see that it very quickly goes to 1. Okay. So it will give me value greater than half and very close to 1. So it will give me something very close to 1. Okay. And if my X transpose W is less than 0, right? So then will be 0 if X transpose W is less than equal to 0. It will be approximately equal close to 0. Okay. So this S of X, that is the sigmoid function, helps us map these values to 0, 1. Okay. So in logistic regression, our goal is to find weights W. So W over here would be W1, W2, W0, and that kind of a vector, such that S of W or X transpose W is equal to 1 for all, let's say, purple cross, and S of X transpose W is 0 for all green circle, let's say. Okay. So we had a loss function that could tell us how much error we are making in case of linear regression. Okay. So for classification also, we have many loss, but the most intuitive one that I'm going to introduce today is called 0-1 loss. Okay. So you have some data point x comma y, right? Now prediction you are making via S. Okay. So your loss between S of X and Y is given by, so this loss value is 1 if S of X is not equal to Y. So if your S of X is telling that your value is 0 and your actual value is 1, then you should make an error of 1. Okay. And if your S of X is equal to Y, so if you are making correct prediction, you are getting 0 error or 0 loss. Okay. And the overall loss can be calculated by a loss between S of Xi comma Yi. Okay. From I is equal to 1 to m, and again this scaling you can do. Okay. So yeah, a lot of things I said, Okay, but the goal is that this is your function. Okay, now I have came one way starting from writing it as a points on two side of line. I'll go other way now so that it is clear for you. Okay, so let me try this way. So for linear regression, you had a function of form f is equal to w naught plus w1x, right? Similarly, when you try to do logistic regression, you have a function of, so if you take x as an input, you will have a function of form 1 upon 1 plus e to the power minus w naught plus w1x. This is the function that you will have in logistic regression. Then you have your losses, right? Over here, your loss was summation I is equal to 1 to m, 1 by m, f of xi minus yi whole square. Here you will have 0, 1 loss. Okay. And you want to minimize this loss. So when you minimize this loss, what happens is s of x gives you 1 for all value so that your w transpose x is greater than equal to 0. Okay. And it gives you 0 for all x such that w transpose x is less than equal to 0. Now, what does this condition mean? This condition means that on your plane, if you plot, so this is your w, let's say this is your w direction, and this line would be w transpose x is equal to 0, right? Then on one side you have data point of one type, and on other side you have data point of other type. Okay. Is the idea of logistic regression clear? If you have any doubt, you can please ask. I have gone a bit theoretical and more intuitive rather than how to implement it, but if there is any doubt, please ask. So why do we use such sigmoid function? We want to use such sigmoid function because we want values between 1 and 0, right? And we want values close to 1 for all those points for which x transpose x is greater than 0. The idea again is pretty simple. You want to find a line. On one side you have all the ones, and other side you have all the zeros. Okay. And you can obtain 1 and 0 by passing that w transpose x via this sigmoid function. Okay. I hope I was able to make it clear. Okay, so few more things. I have many more things, but I think I can do this gradient thing later on. We have this gradient covered in later week. I think it's 7th or 8th week. So there we will discuss this in detail. Right now, what we can do is we can do something like this. Okay. So the classification example that I gave you initially, okay, had so the example that I gave you was we had some voter data and we wanted to predict which party will it vote for, right? So there I mentioned your party can include BJP, let's say Congress or Aam Aadmi Party. But you can definitely see that the list from which you have to choose is more than two. Okay, so in the discussion that we have, this sigmoid or whatever logistic regression, that discussion we had, here we had only two choices to make. Either we want purple cross or we want green circle, right? Here, when you have real world example, you can have more than two classes. Okay. So in classification, you can either have two classes. This is called binary labeled setup. Okay. And this is when you have more than two classes, there are again two bifurcation. One is called multi-class, one is called multi-label. Okay. There is a slight difference in it. Okay. So in multi-class, you have more than two classes. Okay. And your value can be any of these classes. in multi-label, same data point. So again, you have more than 2 classes, and same data point can have more than one label. So I'll give you an example. Okay. So example is, let's say you have all products on Amazon. Okay. And you want to classify them into some classes. Okay. By class, I mean whether it's a electronic item. Okay. So whether it's an electronic item, it's stationery. Okay, these are your classes, or it's home decor. So you have all the categories that you have on Amazon. If you go some any day on Amazon, you have these kind of categories on Amazon. Okay, so you want to predict which product should I put in which category. Okay, but if you take an example of a light bulb, okay, let's say this is your bulb. This is how we used to draw it in physics, right? So if you take example of a bulb, it can come into electronic as well as home decor. Okay, so you can use this Diwali lights that you have, Diwali bulbs. That is also used for home decor, but it is also an electronic item. So they should list it in both of these. Okay, so if you look at this bulb, this should have both the labels. So it should have electronic also, stationary it is not, it should have home decor also. Okay, so this kind of setup is called multi-label setup, and in which you have only one label to every data point is called multi-class setup. Okay, this is just for your information. Okay, so we just discussed how we have like how do we deal when we have two classes, but how do we learn when we have more than two classes? What kind of method should we use? What should we do? Okay, so there are two ways to tackle that. First one is a bit old, but based on whatever we have learned, this is the most suitable method. This is called one versus rest. Okay. So let's say you have three classes. Okay. Then what you will do is you will create three data sets. You will create three new data sets. Okay. So in first class, so let's say this class are C1, C2, and C3. In first data set, you will relabel class C1 as 1 and C2 and C3 as 0, right? Okay. So, and then train your model based on this. So what will this model give you? This model will give you whether it is of class C1 or it is one of the class C2 and C3. Okay, this is what model will learn. Okay. Similarly, your second data set will have C2 as 1, and then you can have C2 and C3 going to 0. Okay. Similarly, third one you can train as C3 as 1. Okay. And C1 and C2 going to 0. So this trick is called one versus rest because you assign one label to the one of the classes and rest of them you assign to the other class. Okay, and you train all these three. You train three separate models on these three separate data sets. Okay, so you will have three separate logistic regression for all these three different data sets. Okay, now at the time of prediction, first let's say you pass your model with so you pass your data point with this model and it says your class is C1. Okay, then you're done. You know that your class is C1, or it says that your class is 1, sorry. Then you are done. You know that your class is C1. Okay, but it says that, let's say it says that your class is 0. Okay, then you will have class from C2 or C3, right? Then you can do this kind of testing, right? You can pass it through model 2. There, if it says it is from class C2, you are fine. If it says it is not from class C2, then you can infer that it is from class C3 because it was one of C2 and C3. Okay. So this is how you get step by step in one versus rest. Okay. So this was one method. Another method is something that is more common today, which is you output k values. Okay. So you output probabilities for all k classes. So when you do machine learning, there you will see that your output layer has more than two classes. Okay. And you output probabilities corresponding to every class. and then you will predict the class which has highest probability. So this, I think I'm just mentioning it right now, but whenever you will do deep learning course or you will do deep learning, you will see how you have more than two output classes. Okay. So I have some 10 minutes left, and I'm skipping this gradient descent. I want to do a more mathematical thing that is known as likelihood. Okay. This is slightly mathematical, but I want to do this because, like, if you go to any random resource, you want to search linear regression and logistic regression, 90% of the cases, they will motivate it via likelihood estimation. Okay. So this is slightly probabilistic approach. Okay. So even if you don't understand some terms, just ignore it for the time being. When we will do probability, I'll sort of try to revisit it, but I want to give you an idea right now also. Okay. So let's say you have some data points. Let's say this is x1, right? x2 you observe, x3 you observe, and so on. Okay. And you have some idea that these data points might follow some distribution. Let's say you know that these data points will follow normal distribution, or yeah, normal distribution. Okay. Okay. But you don't know. So if some of you know normal distribution has two parameters. One is mu, another is sigma. So based on, if you keep changing your mu and sigma, you will keep getting new distribution. Okay, all of them will be of type normal distribution, but you will keep getting new distribution. Okay, so you don't know what is the value of mu and sigma. Okay, but you know, like, that they follow normal distribution. Okay, you know this assumption. Okay, then using these data points, how can you find mu and sigma? Okay, so what should be the value of mu and what should be the value of sigma? That is what you have to predict. Okay, so what we do is we define something that is known as likelihood. Okay, so what is likelihood? Likelihood, let's say for a given mu and sigma, okay, is probability of x1 given your parameter is mu and sigma. These are all statistical terms, even if you don't know the meaning. What I mean is, if you model your normal distribution using mu and sigma, then what is the probability of this point x1? Okay, for example, I'll just draw an example. So let's say for some value of mu and sigma, let's say your points are like this, here you have 3 points, here you have, okay. And you draw a normal distribution, something like this, okay. And you have a red distribution, which is something like this, okay. So which do you think is a better fit for this data set? If you see, these values peak over here when you have more data points. So this orange one should be a more better approximation as compared to this red one, because red ones peak at a point where they have only 2 data points. Okay. So what do I mean is, so if you are given with some mu comma sigma, let's say you have this green orange, this line, right? This green orange line. Then for every point, you will calculate what is the probability of this point. So this is your probability, this value, height, whatever you get. Okay. And this is the likelihood of that particular point. Okay. And then when you calculate the likelihood of all the points, you take their product. Okay. You take their product. So likelihood of all the points will be product of I is equal to 1 to n xi mu comma sigma. Okay. So you take the likelihood of all the points, you take their product, and your goal is to maximize this likelihood. Okay. So for whatever value of mu and sigma, you get maximum likelihood. That value is called as maximum likelihood estimator. I'm being very, very like rudimentary because I'm not explaining those terms. but we will do it in future weeks. Okay. Maximum likelihood estimate. I'm just giving you these terms because you have done linear regression and logistic regression. If you want to go to some online resources and you want to see something, then you shouldn't be confused about what are these, why are they doing something like this. Okay. So these are your maximum likelihood estimator, and these values will be the ones which will give you best predictions. Okay. Okay. One more thing that I want to mention, if you do some lecture on this likelihood estimator or those kind of things, you will see many people saying that this is my likelihood. Okay, this is my likelihood. I can replace this with log likelihood. So what I mean by log likelihood is that rather than taking L of mu comma sigma, you take log of mu comma sigma. Okay. So you know that log is an increasing function. Because log is an increasing function, maximizing L is same as maximizing log of something. Okay. So if you maximize x square or you maximize log of x square, it is same things because your log is a monotonous function. Okay. That to an increasing. Okay. So many people will replace log by log, sorry, likelihood by log likelihood. And the main motive to do that is, so the main motive is when you take product of your probabilities. Okay. So this is your likelihood, like you take product of these probabilities. So right now I am representing this theta to represent u comma sigma, and y is my data, yi is my data point xi. Okay. So these probabilities are always between 0 to 1. Okay. Let's say you multiply 0.4 by 0.4. What is the value that you get? You get 0.16. Okay. Again, if you multiply it by 0.4, you get something like so this is 4 6, right? So you get 0.064. Okay. So if you have, let's say, 1000 data points, and let's say you are multiplying 1000 with values between 0 to 1, so you will get a very, very small values that will become intractable. Okay. So there is no point talking about maximizing or minimizing such a small value. It becomes very difficult, right? So what people do is when they take the log of this thing, then the product is converted as sum. Okay, sum of I log of E of yi becomes delta. Okay, so that's why in machine learning you will see people replacing likelihood by log likelihood so that they can convert this product to sum and the values don't become very, very small and they can deal with this. Okay. Okay, so this is what I had prepared. I think I was not able to cover gradient descent, but don't worry, this would be covered in a future week lecture. This, yeah. If you have any doubt, you can ask. Like anything, if you have. I know I went pretty fast today. So I'll stop the recording.